Hello friends, today's question. A cubical block of side A moving with velocity v on a horizontal smooth plane as shown, it hits a ridge at point O. The angular speed of the block after it hits O is. So this is a cubical block moving with velocity v, and this is the ridge, and this block is going to hit this ridge and going to pivot. And we are supposed to find out what will be the angular speed of that pivot. So in this case, first of all, let's draw the three-dimensional figure of this cube so that it is much more convenient to understand the things. So this is the cube and it is moving along this surface, and this is the point O at which this cube is going to hit the ridge. This is point O. So obviously it is going to pivot around this edge, and let us suppose that axis along which it is going to pivot, we call that as x prime. So it is going to pivot along this axis, let us suppose with the angular velocity of omega, and this is the center of mass of the object of the cube, which is moving with the velocity v. So it is given that side of the block is given as A. So let us write as initial conditions or given conditions. We are given that side of block, which is cube rather, is given as A. Its velocity, which will be linear, is given as v, and also given that collision occurs at point O. Collision occurs at point O, and let me name this. This is A, this is B, C and D, then this is E, F and G and H. So collision occurs at point O, so which basically means cube will pivot about the edge CG. CG, and which we can say about axis x prime with angular velocity omega. Velocity omega. Now it is also given that, or rather we can say we know that the moment of inertia for the cubical block, you can say moment of inertia of cubical block of side A and mass m is given as, let us suppose, I, which will be equal to 1 by 6 ma square. Okay. Now in this case we are going to use the conservation of angular momentum. So we can say angular momentum before the impact. Angular momentum before impact so initially it is only traveling with the linear velocity v, so we can say that there is no rotational motion, no rotational motion of the cube, so which basically means that angular momentum will be only because of the linear motion. Angular momentum will be only due to linear motion. So you can say that the linear momentum P will be equal to mass into linear velocity, and so we can find out the angular momentum. Angular momentum will be equal to P multiplied by the perpendicular distance, that is r perpendicular. So this will be mv multiplied by r perpendicular, and r perpendicular will be nothing but the distance of the center of mass from one of the edges. Okay, so let me draw it here. So center of mass will be somewhere here, and it is given as a. So this distance of the center of mass, let us call this as O prime. This distance or this height will be a by 2, which will be our r perpendicular. Therefore we can say that our r perpendicular will be equal to a by 2. R perpendicular will be equal to a by 2. Therefore L initial, angular momentum initial, will be equal to mva by 2. So this is our first part. Now we are going to find out the angular momentum after the collision. We say that angular momentum after impact. Let this be question number 1. So like I said, that after the collision, this cube is going to pivot or rotate about the axis, that is x prime, okay, and with the angular velocity of omega. You can say that cube rotate about, yeah, we can say along axis x prime, and we already said that with angular velocity that is equal to omega. Now we said that the moment of inertia of the cubical block of side A of mass m is given as 1/6 ma square, and this will be the axis which passes through the center of mass. Okay, so we can draw this axis something like this, and it will be going and coming outside like this. So let us call this as y and y prime. Okay. We can say moment of inertia about the axis y prime which passes through center of mass, which we already know the formula is 1/6 mi square, that is given as I is equal to 1/6 ma square rather. Okay, so let me draw it here. So this is our x and x prime, and we have this axis which is passing center of mass, which is given as y prime. So we can say that this y prime is parallel with x prime. So axis y prime is parallel with x prime. Therefore we can use the axis parallel theorem in order to find out the moment of inertia along x prime. Okay, and we say the moment of inertia along x prime is given as I naught, and this we already know is given as I. You can say therefore moment of inertia along x prime will be equal to moment of inertia along y prime plus perpendicular distance between the two and its whole square. Okay. Now we can find out the perpendicular distance between the two. So this is our y and y prime, and this we have as x and x prime. This is the center of mass, that is given as O prime, and this is point O, the point of impact, and this is our perpendicular distance. So we can find out, let me draw this here also. So this is our O prime, so this is the perpendicular distance, and this distance from the center of the lower base will be a/2, and this distance will be also a/2. Okay, so we can find out O prime, that is perpendicular distance. So this is our a/2, and this is also a/2. So using Pythagoras theorem, this will be coming as a square root of 2. So the perpendicular distance between the two axes, one which passes through the center of mass and another through which it is going to pivot with the angular velocity omega, comes out as a divided by square root of 2. Therefore, you can write that perpendicular distance, or we wrote it as this one. So we can say moment of inertia about x prime will be equal to, let me write it here, moment of inertia about x prime, which we denote as I naught. This is equal to I naught is equal to moment of inertia about y prime, which we said will be equal to I, plus the square of perpendicular distance, and I forgot to multiply it with the mass, so this will be multiplied by mass m. So this comes as mass, and perpendicular distance is a by square root of 2 and its whole square. Therefore we can say that our I naught value of I we already know, that we found as, or that is given as 1 by 6 ma square plus mass, and this comes a square divided by 2. And if we solve it, we get I naught is equal to 4 by 6 ma square. This is equation number 2. So this is the, and we are going to find out moment, you can say angular momentum final. So L final will be equal to I naught multiply the angular velocity, that is omega. So we get this as 4 by 6 ma square multiplied by omega. Now according to conservation of, this is equation number 2. According to angular conservation, you can say conservation of angular momentum, conservation of angular momentum, L initial, that is angular momentum final, will be equal to angular momentum initial. So we can use equation 1 and 2. Using equation 1 and 2, we get L initial was our m, Va by 2 is equal to 4 by 6 m a square omega. M and m cancels out, a goes with this square, and this comes as 3. So we can say that omega is equal to 3v and divided by 4a. This is our, you can say, angular velocity of the pivot. It was asked as, angular velocity of the block, cube, after it hits O. So this is the angular speed of the block after it hits O. And from the option available, you can say that option number A is the correct option, 3v by 4. Option A is correct. So only main typical thing here is to find out the perpendicular distance between the two parallel axes, and using the parallel axis theorem, rest is only quite easily can be done. So this completes the question. Thank you.